Let's try this again. We'll call it fourth time is the charm. Yes, there's annoying shadow happening here with the setup on a different location, but it'll be all right. I have this 3D dimensional coordinate plane. We're introducing 3D. We are officially arriving in Calc 3, no longer doing review or anything else. Here we are. Remember, this has three components, X, Y, Z. Um, but notice this first type of grid I have for you is lacking that third or that opposite negative portion of the axis. This point right here would be 0, 0, 0. To make sure this picture doesn't get too busy, I'm just going to graph these points to the best of my ability. I'm going positive 1, 2, 3 on X. I'm going positive 1, 2, 3, 4 on Y. And one thing I have to do with that, as I turn this down just a tiny bit, one thing I have to do here is I have to do my best to kind of come out perpendicular as I do these. So I'm going to come out here until I feel like I've successfully reached, kind of a nice point that's straight from here, straight from there. It's not a perfect science. But what I found here, this point, I might call something like P prime. Just to say, hey, this is the image of P. This is the shadow that it casts down on the ground from above. But let's add that third dimension, that third element. 1, 2, 3, 4, 5. This thing's going to climb. 1, 2, 3, 4, 5 spaces. Again, I'm making a 3D picture on a 2D surface. It is never going to be perfect, but it is pretty close there. That is where P would sit. Q, again, the same idea, except I'm counting back 1, 2, 3, 4, 5, 6 spaces along Q, coming out somewhere to match this 3. Again, it's not perfect. It's like I'm tracing this out here. That's my Q prime. And then eventually, as I drop this two Z's, I would have the final image of Q. So that's how I'm graphing 3D points, but let's talk about the beginning of graphing 3D surfaces. First, let's take something simple like a straight line. This y equals mx plus b, we know it starts at 1, 2, 3, 4. It has a slope of 1 and looks something like this. Y equals x plus 4. And again, what that line represents is any number I plug in for the input, out comes the same number plus 4. Any number I put in, out comes the same number plus 4. But in the 3D coordinate system, I ask you a question. If I plugged in 2 for every x, 6 for every y, and 2 for every z, would it come out equal? Yes. If I plugged in 2 for every x, 6 for every y, and 3 for every z, would this equation still remain equal? So yes, there are more solutions outside my field of view. And like it says here, if equations only exist in two variables, it extends infinitely in that third dimension. Now recognize that first quadrant is somewhere out here because this is where my positive x's and positive y's are. This is that coordinate 0, 4 over here, and that thing's going to come slicing through like this. That was a bit much. But I need to extend that height. So I can extend that height up here and up here. And I should extend the height down. Down. So you have this kind of rectangle or sheet of paper cutting through my 3 space. This sheet of paper is called a plane. Lines that are extended into 3D are planes. Planes, P-L-A-N-E. That's a plane. And it cuts my space perfectly in half. And you have to imagine that this direction extends forever this way, and forever down, and forever right and left, if you want to call that up, down, left, right. So that is the generalities of graphing kind of basic things on this. We will dig into this 3 space for a while now, but how do I refer to the areas on this graph? Like, I know this is first, second, third, fourth quadrant. But if I have 4 of those above my z surface and 4 of those in my negative z space, like, what do I call them? That would be octants. And in fact, there's no typical naming convention for octants. The one octant we will ever refer to in this course is called the first octant because everybody can agree on that one, and that happens in the positive, positive, positive octant. Positive x, positive y, positive z. Like this point P exists in that first octant. Well, let's plot a plane. This plane contains every coordinate where z equals 3. So that'd be like 0, 0, 3, 10, 17, 3. Anything that has 3 for its z coordinate maintains this equality and would be part of the infinite number of solutions here. So I would probably just drop down that same kind of shape for my coordinate, my octants. I'd label those axes. And again, I would grab when z is 1, 2, 3 up here. That's when z is 3. And again, it's going to extend forever in the x direction. It is completely x dependent. Independent, sorry. And the same thing with y. It's completely y independent because y has no effect on that equation, equality. So really, again, it's just some bedsheet piece of paper looking thing that sits at a height of 3. Imagine there was just, again, like a bedsheet or an infinitesimally thin sheet of metal that cuts through at a height of 3. That's what you're experiencing here. Well, what about an inequality? Something that says like z is less than or equal to 3? To me, that's just casting a shadow. That's just casting a shadow underneath this sheet. Again, I really can't see underneath that sheet at all. And just continuing that demonstration here, if I set this to z equals 3, you see that sheet. If I flatten it out, and let's say y values do not matter here, y is not a part of my picture, I flatten my 3D image to be a 2D image, this should be just a line, just an infinitesimally skinny line. Obviously it has trouble rendering how skinny that line is. But it's a line in 2 directions. If you laid up infinite lines together, you get this plane, just this sheet of paper, infinitesimally small, again, less than or equal to, gives you this thing where looks like a fish tank because it has bounds. But again, it's just everything below that point 3. Back to my 3D space. Back to my sheet of paper. I'm looking, a rectangular tissue box has vertices at these points. Sketch the tissue box, find the length, find the volumes. So again, I'm just going to slap down a nice coordinate plane here somewhere. To the best of my ability. It doesn't have to be perfect. I'm not expecting you to be perfect. You can see my imperfect lines that are a little bit on my nerves. And let's just throw down these vertices really quick. Pause. Not pause. I should show you how to use this second type of grid. Again, I'm going to go from 0, 0, count 2 spaces back on x, 1, 2, 3, 4 spaces back on y, and up 2 spaces for z. So I'm staying on those corners again, starting at 0, 0, moving 1, 2, 3, 4, 5 spaces on x, back 1, 2, 3, 4 spaces on y, and then up 1, 2 spaces on z. And you can see I have one tip of a corner of one of the sides of this box. And again, 1, 2, 3, 4, 5. 1, 2, 3, 4, and then down 1, 2, 3. A little bit off my page for where I started, but that's all right. So we have to kind of think about a tissue box and how it sits, because obviously I can't just draw a diagonal. That's going to be cutting through the box. I can't just draw this diagonal. I'm cutting through the box. Each side of the box of tissues has a similarity. Either it's sitting similarly in the horizontal position, the vertical position, or has a similar depth. You kind of understand what I'm saying here? If I had a box, right, there's similarities in these coordinates. Like if I were to simplify this to a square on a coordinate grid? Again, if I flattened this image, I know that this would share a common x coordinate, and these would share common y coordinates. And that same concept's going to hold where I'm going to have similar x's, y's, and z's as I go here. And look, that's one set of y values. Well, there's only one other set of y values. It only has so much distance it travels in that one direction. So for my y's, it goes from -4 to 4. That's what this opposing corner over here tells us. It tells us the total y distance that I'm going to travel from this side of the box to that side of the box along my y-axis. My x's, how much variance do I have in my x's? I saw that they had a common x up here at 5. I drew a line parallel to that x equals 5, and so I have that there. Let's think about the other side of my x's. If I kept traveling, I would find 2. Right? This has that alternate x value of -2. I traveled back to so many spaces on y, so many spaces on z. Did I make a mistake? Pause. Nope, just got my corners mixed up. So my x's vary from -2 to 5, and my z's are going to follow that same pattern. My lowest, the floor of this thing, goes from -3, and it goes to a maximum height of 2. So I know that this thing is 2 tall, or 5 tall. I know that it's 7 wide and that it's 8 long. Right there, I can already finish this, right? I found the lengths of the side of the box. I find the volume by multiplying them. 8 times 5 times 7, and I get 280. Last but not least, let's finish the sketch of this box, because if I know it has a height of 5, I can just count down 1, 2, 3, and connect that side of the box. 1, 2, 3, 4, 5. It connects this side of the box. Again, I can push it to this. I know this side is along the front face of the tissue box. And guess what? It has a height of 1, 2, 3, 4, 5. And it would connect along the face, the front of the tissue box. How about the side? Well, how long is the side? Well, that is going to be along my x. And I know my x is 7 long. So I would travel 1, 2, 3, 4, 5, 6, 7. And you can see that it stays in line. And again, I can add that height. 1, 2, 3, 4, 5. Just kind of working between your lengths and your widths and your heights, you can connect that whole box together. And again, like this axis slowly becomes more and more useless as I go through. I'm not really going to erase it, but realize the focus of this picture is the box. And I didn't do a very good 3D job, but I sketched the tissue box as it said. So speaking of planes, speaking of tissue boxes, speaking of how to talk about these things, let's talk about how we can simplify some of the terms that we have here, ways that I like to talk about this. Let's consider this to be a corner of the room. The xy plane, where only x and y coordinates exist, it's always x, comma, y, comma, nothing, is the floor. The YZ plane, that's my right wall, where I only have y's and z's and no x's. And my XZ plane would be over here. It'd be my left wall. And that's where I'd have x's, nothing, and z's. So that's kind of how you can imagine this space. And if I'm going into the negative z's, I'm going through the floor. If I'm going into the negative x's, I'm going through the xy plane. That's one piece that I will admit is difficult, is that what's perpendicular to these planes is always the thing that you're not using. If you want to travel out of that plane, you need to use that perpendicular thing. And that'll be, when we get to equations of planes, we'll need that concept of perpendicularity to go. Here we are, not wasting time. The 2D distance formula is derived from the Pythagorean theorem. right? My Pythagorean theorem tells me x squared plus y squared equals r squared. Oop. A squared plus b squared equals c squared. Did I jump? All right. But that's the idea, is that the circle formula is derived from taking this radius or hypotenuse and dragging it around in that equal distance away from the center. Very bad center. But that's the concept, and I can find distances by, again, expanding this to 3D. All I'm doing is adding another thing under here. This is where we get magnitude. This is where we get length. This is where we get strength or power. Every time, let's just shortcut it a bit. My distance from -3 to 17 is 20 squared. My distance from 9 to 4 is 5 squared. My distance from 14 to 12 is 2 squared. And I don't care if they're positive or negative because I'm squaring them. I get a cool square root of 449. 429. What am I saying? 429. That distance formula will get used over and over again. The concept of the distance formula, finding out the amount of x and y and z that's changing, is used all throughout this course. Next up, I'm looking at the center of a cube is located at -7, -8, -9. Find the 8 vertices. The side of the length of the side of the cube is 4. The only thing I need to think is the center part of the side length? No. The side length is 4, and every side is equal distance away from this. Like, think about this with me, right? I have the heart, the center of this box, but the whole box that sits around it, that's a miserable cube, sits around it. No side directly sits on that center. In fact, from the center to the wall, if I go directly orthogonal, if I stay on my straight x's and my straight y's, drawing those parallel kind of shapes, I know that it would be 2 and 2 to make 4. 2 and 2 to make 4. So see if you can sketch and find some of the coordinates based on that idea. 2 and 2 and 2 and 2 and 2 and 2. Well, that just made a hexagon. Well, yeah, you have some points that are sitting on the side, but those aren't the vertices. I'd have to go over 2, and then I'd have to go 2 more. What? Yeah, because I have to go, to find the positive most corner, I'd have to go +2, +2, +2. Well, what about the negative most corner? -2, -2, -2, right? From the heart of it, I'm going negative, 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 until I find that negative most corner. -9, -10, -11. Well, if those are the corners, that sets my z value solid. That sets my x value solid. That sets my y value solid. And all of a sudden, I can use that same concept of the tissue box, because now everything, I just travel forward in any direction and I'll have another corner. So like if I traveled 4 up from the lowest corner, I would have the top above it, -7. If I traveled 4 on the y value from that bottom corner, I would have another corner and another corner. Another corner would be that bottom from that positive most corner. And the same thing over here, kind of changing these back and forth. Those are my 8. And yes, the picture is a little bit hard to kind of come about, but again, you're thinking, I'm traveling, for the positive most, I'm traveling 2 positive, 2 positive, 2 positive. It actually sits right back where I started. But then if I wanted to find the negative, I would go back to, and down to. right? The orientation of this grid makes it a little bit difficult where those positive and negative line up, but I know that if my side length is 4, I could go 1, 2, 3, 4. 1, 2, 3, 4. And start connecting the sides to my box. 1, 2, 3, 4. 1, 2, 3, 4. I lost count. 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And my cube takes shape. Right? Where I'd have a side length of 4, but I can see how those 2's help me get to the 4's. These will be best done through just, you have to think it through. Thinking how far is it from the center to somewhere? How far is it from this point to that point? All right, towards the end here, I have equation of a circle, which comes from the equation of distance becoming a sphere. And again, in the same way, I'm just adding that third dimension here. This is circle. This is sphere. And here we go. Write the equation of a sphere centered here with this radius. Easy, right? All of my translation memory from Algebra 2 says, well, it's just the opposite. And square that radius. But it says find 4 points along this sphere. Well, I know that when I drag a circle, it's very unlikely that I end up through rational coordinates at all, not to mention nice points. But where can I travel and find nice, clean coordinates? Well, from that center, I could just go 4 straight down. Couldn't I? 3, negative, sorry, 3, negative, I lost my space there. 3 straight down would be negative 12. Absolutely. Well, could I go 3 straight up and hit the side wall of the sphere? Absolutely. And what this is doing, when I plug in these coordinates, it's going to maintain equality because it's going to eliminate 2 of them and save the third. And it's always 3, or negative 3 is the result. I square it, I get it back. So that's kind of where the secret hides here. I don't want to mix and match and go 1.5 this way, 1.5 that way, because the squaring and the distance formula won't work out. But if I went 3 this way and 3 that way, everything would totally work out. Right, 3 to the right, I hit the side. 3 to the left, I hit the side. 3 forward, I would hit the side. 3 forward would be what? 0. And 3 back would be 6. Or however, once you get into 3D, forward, back, left, right, up, down starts to get a little more confusing. I should just write them out, shouldn't I? Yeah, negative 4, negative 9, negative 4, negative 9. Here we go, last but not least. Find the equation of this sphere in standard form. What a beautiful problem. Zoom in a little bit for this last one, because it is so nice. Again, if I'm trying to get to this form, I'm trying to get from something that looks like, let's just combine some like terms for a moment, or group like terms. Right, to go from x squared plus something x to this, I need to complete the square. I need to make it so this becomes a square term. Half the middle is 1, squared is 1, and I add that to both sides. Half the middle is 4, squared is 16, I add that to both sides. Half the middle is 2, squared is 4, I add that to both sides. And now I'll be able to finish, because this side, zoomed in a little too much, this side makes a cool 49. Shocker, a nice number. But here, half of that is 2. Here, half of that was 4. Here, half of that was 1. And it just comes out that smooth. Completing the square is negative 1, negative 4, and 2 with a radius of 7. All right, folks, I hope that was good for you. Hurrah, huzzah. That was way too long on these notes. It will be faster next time.